Hey everybody, Dr. White here again, continuing our discussion of arc length and surface area. Now we're going to look at the surface area of a solid of revolution. So imagine that you've got some piece of a curve y equals f of x from x is a to x is b, and say you're just revolving around the x-axis and you get a little solid of revolution. And we're wondering what's the surface area of the solid. Now, by the surface area, I don't actually mean all of the area of the surface, because there's like a circular face on the left-hand side at x is a, and there's another circular face on the right-hand side at x is b. Those are pretty easy to find the areas of because you just need the radii. I'm interested in the side face, this curvy side face stuff. When I talk about surface area of a solid of this sort, I just mean the surface area along the sides. Can we find a nice formula for it? Well, here's our idea. We're going to use strips again. So we'll use a little vertical strip of some tiny thickness dx at some point x between x is a and x is b. Okay, and so we head up from the x-axis to the curve, we get our strip. And I want to magnify that strip for you a little bit as you revolve it around the x-axis. So coming over here, we get a little magnified picture of the little teensy-weensy solid that you get by revolving that strip. And so I imagine it starting at x and going to x plus dx along the x-axis, where dx is this tiny, tiny, tiny little thickness. And the height has varied from an f of x to f at this other place. I guess you could call it x plus dx. And so if I draw like a straight line from those two heights, then I've got pretty much the little solid. Once I revolve that around, I got pretty much the little solid. So we get this little shape here. And I'm going to turn that shape flip it over onto its larger base. So it looks like this. The shape is actually called a frustum. The reason it's called a frustum is because it's kind of like a cone. Here's this circular base, and you can see the sides coming up, and they would like to come to a little point, maybe somewhere up here, but it got chopped off at this other level, and so it's frustrated. It can't really be a cone. It's a frustum. So anyway, mathematicians have found a formula for the surface area along the sides of this frustum. So not the top circle, not the bottom circle, but just the side stuff. And that surface area is equal to pi times the sum of the radius of the lower circle, r1, the radius of this upper circle, r2, times the length of this straight line that you can drop down anywhere along the side. Call it S. Okay. So that product makes the surface area. So what we would like to do is take a look at our teensy-weensy little frustum here, and I'm going to draw another picture of it, but without the rotation being shown. Okay, so here's my little picture without the rotation. And I'm focusing in on that straight line that I've got above the x and the x plus dx. So what we have is our right triangle, very much as back in the arc length situation, a little right triangle where the hypotenuse is the straight line that's approximating the actual curve between the 2 points. The base is a dx, and just like with the arc length, the height is going to have to be f prime of x times dx in order to get the slope right. And so then the Pythagorean theorem comes into play just like before. You can factor out a dx, take it outside the square root sign, and you get this little formula for that tiny little side. So in our tiny little thin frustum, if I go back and set it on its end again, we have an upper radius of f of x, a lower radius of f of x plus dx. That thickness is the dx here, and the s side is this square root stuff times the dx. And so our teensy-weensy little surface area is pi times the sum of those two radii times this s. And when I look at f of x plus dx, I think to myself, well, hey, x plus dx is hardly changed from x. And so f hasn't had much time to change either. So f of x plus dx really must be just about f of x. I'm just going to go ahead and throw that in. And so I've got two f of x's here. And so the little formula for the surface area ends up getting written 2 pi f of x times the square root times dx. And so the total surface area, of course, would be the sum, the integral of all those infinitely small surface areas all the way from x is a to x is b. Great. So let's just try one example, and we'll just compute the example out far enough to see that, yeah, you could finish the problem. So imagine the curve y equals x cubed from x is 0 to x is 2, and rotate around the x-axis. So this shaded area here being rotated around the x-axis, find the surface area of the curvy side of it. So by our formula, this is going to be the integral from x is 0 to x is 2 of 2 times pi times our f of x, which is an x cubed now. And then we need the square root of the 1 plus the f prime squared. Well, the f prime would be 3x squared, and we're going to have to square that. And then we got our dx on the outside. So 3x squared squared is a 9x to the 4th. And so we look at this thing and we're like, you know what? There's an x cubed out here that is almost the derivative of 1 plus 9x to the 4th. So a u substitution should work just fine for us. So let's let u be 1 plus 9x to the 4th. Then du would be, well, the derivative of 1 is 0. The derivative of 9x to the 4th would be 36x cubed. So du would be 36x cubed dx. So dx is going to be du over 36x cubed. Also, since we're doing a u substitution, let's go ahead and change the limits of integration to be from x's to u's. When x is 0, this is going to turn out to be a 1. U will be 1. When x is 2, this will be 1 plus 9 times 2 to the 4th, which turns out to be 145. And so our integral becomes the integral from 1 to 145. I've still got my 2 pi x cubed here, but now I've got a square root of u instead of the square root of 1 plus the 9x to the 4th, and I've got this stuff instead of my dx. The x cubes cancel, as I imagined they would, and you get an integral that you can proceed to work with. Who really cares what the actual answer is? The idea is we can get it. So that's just the one example with surface area. The drama of it is really very much like the dramas that you might get when you're doing arc length. So that's all for now. See you later.